All right, let's jump right in. We're going to do a deep dive today on a topic that's frankly critical for any engineer looking at AI. And that is, how do you actually train a machine learning model for structural design that you can trust? We're going to walk through the exact protocol, step by step, for creating a model that gets design requirements right based on ACI 318 standards. You know, it really all comes down to this one question, doesn't it? As a structural engineer, your stamp is on the drawings. Your reputation is on the line. So, if you're going to use an AI tool, you have to be absolutely sure it's not some kind of black box. It needs to be a reliable partner. This whole explainer is about the how, the practical process for building that trust from the ground up.
So we've got a pretty clear 5-step plan. First, we'll nail down what a trustworthy AI even means in this context. Then, and this is huge, we'll talk about splitting up our data. After that, we'll get into the specific numbers and metrics engineers actually care about. Then comes the final exam for our model. And to wrap it up, we'll see how you package the whole thing for real-world use.
Okay, step one. Let's be really clear about our goal here. The point is not to build a model that can just memorize the answers to 10,000 design problems we already solved. A model that only memorizes is, let's be honest, completely useless for new projects. The real goal, the holy grail, is creating a model that can generalize.
And what exactly is generalization? Well, it's the model's ability to actually learn the underlying principles from the data. It's not just spotting patterns. It's truly understanding the physics, the relationship between loads, spans, and materials, so it can give you accurate answers for brand new designs it's never seen before. That, right there, is the difference between a cool party trick and a legit professional engineering tool.
So, how do we get there? How do we build a model that can generalize? Well, it all starts with our second step, and you could argue this is the most important one. To trust our model, we have to test it fairly, and that means you can't give it all the answers to the test beforehand. The absolute foundation of this entire process is how we partition our data. This three-way split is a super simple but incredibly powerful idea. It's just standard practice in professional machine learning. You take your massive master data set of, say, thousands of engineered examples, and you chop it up. 70% of it is for training, 15% for validation, and a final 15% gets locked away for the final exam. The best way to think about this is like studying for the PE exam, right? The training set, that's your textbook. It's where the model does all its heavy lifting, figuring out how inputs like span and loads lead to outputs like rebar area. The validation set, that's your practice quiz. You use it while you're studying to check if you're actually getting the concepts or if you've just accidentally memorized the textbook pages. That's a huge problem we call overfitting.
And that brings us to the test set. This is the real deal, the final, proctored exam. This data is kept under lock and key, and the model never, ever sees it during its training. How it performs on this set is the single most honest, unbiased measure of how it's going to perform out there in the real world. This is where trust is truly won or lost.
Okay, so our model is training away, and we need to check its work. But just saying it has 99% accuracy is totally meaningless for an engineer, right? We need specific metrics that measure error in a way that actually relates to the physical world we work in. First up, the most intuitive one, mean absolute error, or MAE. It's super straightforward. It just answers the question, on average, how far off is the prediction from the correct engineered value? It gives you a direct sense of how big the typical error is. So, for instance, if you get an MAE of 25 square millimeters for rebar area, you know that on average, the model's prediction for AS is off by that much. That's a number an engineer can look at and immediately understand if it's within an acceptable tolerance for a project. Next, we've got root mean squared error, or RMSE. It's kind of like MAE, but it has a built-in alarm for big mistakes. Because it squares the errors before averaging them, it penalizes huge blunders way more than small ones. This is really our safety metric. It's the red flag that tells us if the model is making some occasional really bad calls that could be dangerous. And our third key metric is the coefficient of determination, which everyone just calls R squared. It's the score from 0 to 1 that tells you how much of the variation in the answers can be explained by the model. To put it simply, it's a great measure of how well the model's predictions fit the real data. So what does a good R-squared look like? Well, seeing a score like 0.98 is just fantastic. It means 98% of the variation in the design results can be explained by the model. That points to a really strong, really reliable model that has definitely learned the right lessons. All right, so the model is trained and the numbers are looking solid. But we're not done yet.
As engineers, you know the drill: trust but verify. The last part of our validation isn't just about numbers on a spreadsheet. It's about looking at the errors with our own eyes to see if there are any hidden problems.
You know, when we plot the model's predictions against the actual correct values, what we're hoping for is a perfect one-to-one line. Every single point would fall neatly on a straight, diagonal line. It's a really simple visual check, but it's incredibly powerful. We mostly use two charts for this. The first is that predicted versus actual scatter plot. It gives you a super fast way to see how it's doing. Are the dots all clustered tightly around that ideal line? Or is the model, say, always under-predicting for larger spans? The second chart is a residual histogram, which is just a graph of the errors themselves. For a really good model, this should look like a bell curve centered right on 0. That tells us the errors are random and unbiased, which is exactly what we want.
So, we've trained it, tested it, checked its metrics, and visually inspected its performance. The model has passed with flying colors, and we've deemed it trustworthy. So now what? How do we actually turn this thing into a practical tool that we can plug into our design software?
Well, the process is actually pretty straightforward. First, we save the fully trained model, basically its entire brain, with all the optimized weights it learned along the way. Then, through a process called serialization, we package that brain into a single portable file. And that self-contained file can then just be loaded into the main design application, ready to go, providing instant and, more importantly, trusted design predictions whenever you need them.
And that's the protocol. It's a rigorous, transparent process that's all about building a tool an engineer can actually understand and rely on. It takes AI from being this mysterious black box and turns it into a verifiable part of our engineering toolkit. So the real question it leaves us with is this. Now that we have a blueprint for building trust, what's the next big engineering challenge you'd want to solve with it?